In this video, I'm going to talk about the pn-junction and its properties, in particular the breakthrough voltage and so on. So the pn-junction is somewhere inside, and I would like to test it. So first we have to design the circuit to do it. But the major problem is that to test the breakthrough voltage, I need very high testing voltage, let's say 5 kilovolts. So to build the circuit, we do the following. I'm using a small signal sine generator. I can control the frequency. Then I put signal to the audio amplifier, so I have some decent power out. So the audio amplifier works up to almost 0.5 megahertz. It's sufficient bandwidth for my purposes. So after that, I put the magnified amplified signal to the transformer. So this transformer is from the old TV, LCD TV. It's used for the back illumination of the screen. So after this transformer, I have the testing device. So in this case, I have a diode, and I have the resistor to limit the possible current coming through this device. After that, I'm going to connect it to the oscilloscope. So I have X and Y, two channel oscilloscope. So the first channel is going to show us the voltage on the diode, and the second one is going to show us the current flowing through the circuit, as the current is proportional to the resistance. So this is the circuit. So once again, this is the circuit. It's very simple. So I expect to have the secondary of this transformer approximately 5 kilovolts, and I can control this voltage using my audio amplifier. So I have the potentiometer to control the signal, so I can control the output voltage. So then this voltage is applied to the diode connected through the resistor, which is inversely, the current through this resistor is inversely proportional to the value of this resistor. And as a result, I'm going to see this graph. So basically, if I have the sine wave at the output, I know that the diode is switched on when I cross the critical voltage, approximately 0.2, 0.7 volts, depending on the type of the diode. So once this diode on, what happens is that the voltage drop across this diode is very small, approximately 0.2, 0.7 volts. So on the graph, I'm going to see, like if I look down there, I'm going to see that I have the flat line, very small voltage, almost unnoticeable with regard to the other voltages. So once the diode is off, what happens? The resistance of this diode becomes infinite. So I will see the voltage on this diode exactly equal to the voltage of the power supply. So let's say 5 kilovolts, whatever voltage I have. So the diode is going to work in those two regimes. So it's on and off. So when it's on, we have the flat line on the voltage. When it's off, we're going to see the voltage jump on the diode, and the current is going to behave in the opposite way. When it's on, the current is proportional to the voltage divided by the resistance. So it's going to look like this. And then when it's off, there is no current flowing through the device, so we have the zero current. So that's pretty simple. And one remark: if you look at the time on and time off, we conclude that the time on is a bit shorter, because we have to, like if we have a perfect sine wave, we have to overcome this small voltage, 0.77 volts. So it's going to be a bit shorter, but almost the same. But in the reality, I'm going to see actually something different. I was surprised to see. So we'll see it a bit later. So now going from the paper and threw it to the actual device. Boom, boom, boom. And here is the signal generator connected to the audio amplifier. And the audio amplifier is fed with the power from this beautiful little impulse power supply. So after that, the signal goes to the transformer. So this is the transformer from the old LCD TV. So we have the primary and we have the two secondary windings. So I use one of them. So the secondary is connected to the breadboard, where I have the diode and where I have the resistor to limit the current. And here's the oscilloscope probes which are going down there. So I have the oscilloscope. And finally we can go and look at the graphs on the computer. Now let's take a look at the oscilloscope. So here is the screen. The yellow line is voltage across the diode, and the blue line is current through the diode. So it's actually proportional to the current. So the peak voltage at this moment is 9 volts, and I have a Schottky diode at test. So let's increase the voltage on my audio amplifier. So you see that the voltage is increasing, and I know that this peak corresponds to the diode being in state off, and the flat line is when diode is open. At this moment I have a relatively high frequency, around 10 kHz, so the waveforms are a bit strange, but we will look at the different frequencies a bit later. So at this moment I can play with the amplitude of the signal applied to the diode, and the goal is to see when I have the breakthrough happening at this diode. So when this voltage, which is basically the voltage across the closed diode, is increasing and becomes significant, we're going to see that the diode opens up and the line becomes flat. So let's see it once again. I increase the voltage up, and now I have the flat line. So meaning that at this moment we have the breakthrough on the pn-junction. So once again, and the peak voltage around 29 volts, 29 volts. So meaning that you cannot apply higher voltage to the Schottky diode of this type, otherwise it's not going to resist, not going to be capable to protect your circuit or rectify the signal. And what else can we do? We can look at the Zener figures and try to get the same graph as we have in the books. So at this moment I'm increasing the voltage, and I can note that we have very strange shape. So this thing is going to correspond to the usual graph you can find in the textbook. So it's flat line initially, and then we have exponential growth. So it's when the diode is open. So once again, so when we have voltage below 0.9 volts, it's going to 0.2 volts for the Schottky diode approximately. It's closed, and now it's open. So we have the current, and then we increase the voltage even more, and boom, we have the limit. So now we have this thing. So we have the voltage is across the x-axis and the current is across the y-axis. So we see that we have those two limits. So this is for the open diode, and this one is for the closed diode. And here is the line, it's going like this. But actually what happens, we have a small hysteresis. So the curve goes like this in one direction and then goes back over this path back to the initial condition, initial state. So this is pretty strange. So I was not expecting to see it. And at smaller frequency, it does not look like this. It's actually more like a single curve. I have the graph, I will show them in a bit. But from this graph we can conclude that we see that the voltage is never exceed those two lines. Whenever it exceeds this limit, we have the current growing very rapidly, basically goes to the infinity. And just for the reference, I'm going to show the curve I was expecting to see. So this is the curve. So this is the direct connection of the diode. So once we overcome this voltage, approximately 0.7 volts for different types of diodes, we have this exponential growth of current. And then if we go back in the reverse, if we switch the polarity and go in the opposite direction, we're going to reach this limit, which is called breakthrough voltage, after which we have the avalanche, basically, we have the increase of current in the opposite direction. So if you look at this graph, so when the diode is on, we have the flat line, when it's off, and for the sine wave signal we have the graph going like this, but whenever we exceed the breakthrough voltage, it's going to cut it at this breakthrough voltage. So once again, on the oscilloscope, well, I lost my mouse. In order to understand this hysteresis curve, we have to look at the operation of diode more precisely. So I have done a few measurements previously, and now I'm going to just show you the results. So again, so yellow line is the voltage across the diode, and blue line is current in this circuit. So at low frequency, around 100 Hz, we have 100 Hz. We have this type of patterns. So the signal is, when the diode is off, we have basically the voltage proportional to the power supply. When the diode is off, when the diode is on, we have the drop on the diode equivalent to the direct voltage across the PN junction, 0.2, 0.7 volts, and then it repeats again. And the current is the opposite. When the diode is off, we have the zero current. This does not conduct any current. When the diode is off, the yellow line is close to zero, so we have the current. Again, repeating the shape of the applied voltage divided by the resistance in the circuit. So at low frequency, we know that the on and off time approximately the same. So the length of this moment is equivalent, almost the same as the length of the moment of the time duration where the diode is on. So off and on time approximately the same. Now we're going to increase the frequency. So this is 1 kHz. So we know that we have a bit longer on time, in that case at 1 kHz. If we increase the frequency to 10 kHz, so now we see that the time on is almost 2, maybe 3 times the duration of time when the diode is off. So why this is happening? It's not supposed to be like this if you just use a simple theory, but in reality what I'm thinking that maybe the PN junction is charging, so it's not charging when the diode is on, so it's not so easy to switch the diode off. So we try to switch it off, but we cannot. It's still like the current still is flowing, so maybe this is the duration of time of PN junction discharge or whatever. We have to do research on this subject. It's probably something trivial, but I might be mistaken about this. So anyways, So we see that now the diode operation becomes not symmetric. So the time off is shorter than the time on. So the diode on the time on behaves. So the diode behaves a bit differently when we have the voltage in one direction and then we have the voltage in second direction. So that's explain probably why do we have this hysteresis. So this is pattern I've seen. So if we decrease the voltage, have this pattern, and here's the pattern. So what happens in one direction? So this curve on the graph. So this curve on the graph goes like this, and then it goes back like that, and then again it goes like this, and so on. So the process repeats itself as we have sine wave. So, but what we see here, that in one direction it goes like that, and when the polarity is flipped, we have a different path, and then it repeats. So we have this circulation and hysteresis, which is pretty interesting, I think. So on those graphs we can see what happens when we increase voltage gradually. So this moment the diode works in the appropriate regime. So we have the time off and time on, and we have the current. We probably have some discharge current for the pn-junction and so on. So if we increase voltage a little bit, we basically reach the limits of the diode at this moment. And if you look at the ECG figure, we have this pattern that we've seen before. So if we increase voltage even higher, so at this moment we have reached the breakthrough voltage. So we have the flat line from both sides in the direct and reverse direction. And we have the current basically a sine wave because the diode is open, we just cut a small piece of it. And those ECG figures we have this pattern. So basically the voltage, the maximum voltage in forward and reverse direction is that, and defined, in this case it's 29 volts, and is defined by the diode type. For the Schottky diodes it's a bit smaller. And here is the voltage along this axis. And we know that the same kind of size, the same length of this arrow. And we have this nice pattern. So because of the high frequency we have this small hysteresis. So basically it goes like this and then goes back. And if we reduce the frequency, so at this moment we have frequency 8 kHz, in this graph it's 8 kHz, so if we decrease the frequency, we will see something like this. So now it's kind of look the same. So we this figure is almost there is no hysteresis. So in this case, at small frequencies, and the shape of this figure is similar to that figure. So I guess at small frequency we can just remove this strange effect. But in my case, smaller frequencies are not good for the device, for the system, because the transformer is not capable of multiplying small frequencies. So in that case we have like a strange shapes. But anyways, the key moment is that at small frequencies we have patterns similar to the textbooks. If we increase the frequency, we're going to have this hysteresis curve, which was a bit surprising to me. Okay, so let's take instead of Schottky diode, usual diode. So this is Schottky diode, and here is the ultra-fast diode. And we know that the pictures are very similar, with small differences. So the Schottky diode and the usual regular diode behaves in the same way, except that the breakthrough voltage for the regular diode is significantly higher. In this case, around 150 volts. But the shape like and the pattern like is almost the same. And yes, and the direct voltage for the Schottky diode is smaller, 0.2, 0.4 volts. For this one is 0.7 volts. So that's the only difference. So let's now let's play with some different devices, not just diodes. The next device is Zener diode. So this is the device. Well, it's not easy to see it, but anyways. So this is the device, and the device has characteristics very similar to usual device. So except that you have to connect it in the opposite direction and use the breakthrough voltage. And you do it to get the voltage stabilized. So let's say if you increase a voltage a bit, you're going to significantly increase in the current. So the voltage is going to be held close to the breakthrough voltage. So define the circuit like this. So let's go to the oscilloscope screen. So again, yellow is the voltage in this device and blue is the current. So increase the voltage a bit. So in those cases the diode is closed, the Zener diode, and now the diode is open, so we have the current. So let's increase the voltage a bit more. Okay, so now we see that we have the breakthrough voltage at this point. So and the breakthrough voltage is 16 volts, maybe a bit less. Well, 16 volts. So this diode is designed to stabilize the voltage at the level of 16 volts. And then, as usual, so nothing special for this type of semiconductor, just usual diode. And let's look at the CG figures. So that's what we have. Again, we have seen before. So I increase the voltage a bit. And a bit more. Okay. So this is the reverse breakthrough voltage, and this is the direct voltage. So once again, the only difference for this device that you have to connect it in the reverse position, so that you use not this 0. something volt, but you use the opposite voltage, which is say 16 volts in this case. But if you don't have the Zener diode present, what you can do, you can take a Schottky diode. It's probably is going to be the voltage is going to be around 20 volts, 30 volts, 50 volts. So you can take a small signal diode with a breakthrough voltage around 150 volts, 200 volts. So you can use other devices for the same purposes. The next element is DIAC, diode for alternating current. So here is the element. On the circuit it defines like this, so this is the symbol for it. Same is here, so you can look at this as if you have two diodes connected in opposite direction. So this is the theory, very nice interesting curves. So we have the voltage here and we have the current. So we see that the voltage is increasing until it reaches the breakthrough point, and then we have slow decay to the forward voltage. The same is for the opposite side, because we have two of those connected in opposite directions. I received similar graph from the oscilloscope, it's a bit different. So if you look at the curve, so what happens, so this curve is that one. So we have increase in voltage, then we have increase in current, then falls down using opposite path, and the process repeats again. Let's look at the oscilloscope. So the yellow line is the voltage across this device, and the blue line is the current. So at this moment peak to peak is 14 volts. I'm going to increase the voltage. So at the voltage, at the peak to peak voltage equal to 33 volts, we have this process start to happen, and then increase a bit more and more. Yes, so what we say that we have the flat lines, meaning that the device is on in both directions, and the voltage is 35 volts. So once you have the voltage higher than 35 volts, this device is going to be open in two directions. You can also look at the Zener figures. So in that case, that's the figure that I showed just a moment ago, and if I decrease the voltage, it's going to collapse to the flat line. So in that case, the device is completely closed, so there is no current, so there is nothing on the y-axis, there is only voltage across the x-axis. If we increase the voltage, so we increase the voltage, and we have a small current spikes on the sides. Well, in a sense, it's very similar to what we have on this graph. So we have those spikes here. So let's increase the voltage a bit more. And now we have the split. So we have the hysteresis again, for whatever reason. And also we have very nice feature, like loops, small loops. Oh, it's nice to watch it. So anyways, so this is the device. Is this magic inside? In conclusion, I have met my objectives. I have tested several diodes, different types of diodes. So I look at the regular diodes, ultra-fast diodes, Schottky diodes, DIACs, Zener diodes, and so on. So I should note that it's good to know actually what is inside of those small pieces, because they kind of look the same, but they're all different. Especially for the Schottky diodes, the breakthrough voltage is critical and not very high, and if you put the Schottky diode without knowing the limits of application, you might burn a circuit entirely. So it's good to check actually what's inside, what is the breakthrough voltage. Data sheets are good, but you have to pay a lot for the parts which was tested for you. Some of those things I bought from China and pay like $1 per 100 pieces. Maybe they do not my specifications, but you can test those devices and know actually the limit of application. Anyways, like I feel safer when I know what are the limits for those parts. So the DIAC was especially interesting device, very nice curves for the voltage versus current dependence. And so this guy actually started this project to test this one. However, it's broken, so the pn-junction is burned, so just a straight connection. So this device is used to control very high currents, hundreds of amps, has 3 inputs, and I think I would have to find a replacement for it, unfortunately. So we'll do it in the next video.